All right. Can everybody hear me up there? Are we good? Okay, thank you. Louder? Is this better? Can everybody hear me up there? All right. So last time we talked about computational universality. We talked about context-sensitive languages. And just again, to put it in context, this is the Chomsky hierarchy. There's the context-free languages, there's the regular languages, context-sensitive languages, we talked about them last time. And today we'll start talking about other complexity classes, parameterized by space and time requirements. So it turns out between these classes, there's many other classes. In fact, there's infinite hierarchies of classes right in between all of these other classes. So there's an infinite number of classes between polynomial time and non-deterministic polynomial time, between context-sensitive and context-free, between decidable and context-sensitive, and so on. So now you're seeing more fine nuances of the Chomsky hierarchy, and things will get more complicated and subtle. So hopefully you wrapped your mind pretty tightly so far around the concepts up to now, because now we're not going to just be concerned with what's doable and what's not doable, what's decidable and what's not decidable, recognizable and not recognizable, but how long it actually takes. How much space, how much time, how much other resources we consume while we compute. Because when we compute in real life, we got to compute efficiently, right? We don't just want to say, oh, it's possible, it's decidable, and walk away. We need a fast, efficient algorithm that can finish within our lifetimes, or within the lifetime of the universe, for that matter. Because some algorithms will take even longer than that to solve certain problems, as we'll see. Any questions before we head deep into all these subtleties? Okay. So let's start talking about resource-bounded computation. So again, before we asked what can be done and what can't be done, what's decidable, what's not decidable, what's possible to do and what's impossible to do. But now, among all the things that are possible to do, we'll ask how efficiently can we do them. We'll start splitting these hairs of resource usage. And by resource, we mean usually either space or time. So space is how much memory we use, how much tape in case of a Turing machine, in case of actual real computers, how much memory usage, how much disk usage, but memory in general, space. Time is how many time steps you consume before the computation is done, and you get your answer, the number of state changes in the computation. So this applies to Turing machines, this also applies to programming environments, and the other computers that we build or even theorize about. Things happen in discrete fashion, right? Every clock tick, you make an arithmetic operation and you keep going until you get your answer. So that's the time steps that we measure, essentially state changes. And by the way, before we even get further into that, just so you don't think time and space are the only two resources that we tend to conserve or measure or care about, what other resources do you think we want to conserve while we compute, besides execution time and memory usage, aside from space and time? What else might you guess we're trying to conserve? Yeah. Power, yeah, especially for handheld devices and smartphones and anything that is not tethered to a power source where power is scarce. You want to conserve battery life, that's an advantage. So you want to compute in ways that conserve power. What else might you be wanting to conserve while you compute besides space, time, and power? I'll give you a hint. There's dozens of other things you might want to conserve, not just one or two. What would you guess? Some of them are more abstract. Some of them are more high level. Yeah.
How many external resources or libraries do you need?
Yeah, how much extra code you need. Or speaking of code, when you program, when you construct the algorithms, what might you be trying to conserve if you're an actual company that's trying to make a profit? Not a hard question, right?
So I guess it's like corollary power.
Heat, power is related to heat, but heat could be different than power. As you program, what might you be trying to conserve?
Life
Lines of code,
Programming time.
programming time, manpower, right? Length of code, time to debug. Sometimes you want to write a longer program that's more straightforward, easier to debug, easier to write, than a more convoluted, small piece of code, but it's more cryptic and hard to code, it's hard to maintain, it's hard to understand when you look at it. So length of the program is not exactly correlated to the amount of effort required. Sometimes a short program requires a lot more effort than a long program. How many have seen that experience? Okay, good. So for example, that exercise I gave you for extra credit, write a program that prints itself out. How many have done this exercise? Wrote a program that prints itself. How many lines of code did you use in that exercise, roughly?
20.
How many? 20? Yeah. And how long did it take, by the way? Usually 20 lines of code take a few minutes to write, right? Or half an hour or something. And by the way, this exercise could be done in just a few lines of code. By few, I mean you can count them on one hand. In fact, if you do it in C, you can write one line of code that does that. Less than a tweet, less than 100 characters. And that exercise could take many hours, and justifiably so. Some people may work on this for days, on these 5 lines of code. So point is that size of program is not necessarily correlated to how long it takes to write that program. Thomas Jefferson once famously said in a letter, as he started the letter, he said to his friend, you know, I apologize for writing such a long letter. I would have written a shorter one if I had more time. Think about that. Okay, what else what you might be trying to conserve while you compute besides space, time, power, lines of code, and person effort? Like wild guesses. Almost everything is correct here, yeah. Financial cost, you know, dollar cost, which is related to man effort as well, or person effort. What else? Let's say you're writing a sort subroutine. You're trying to sort numbers, and your numbers are on disk. That's a hint, yeah. Disk usage, disk I/O, right? How many times you have to go from RAM to disk while you compute some function or some algorithm or some subroutine matters a lot, because disk is a lot slower than CPU. So you want to store as much of it in RAM as you can, rather than to go out to disk every time you need a number to work with. Now it's not always possible to do that, you know, to the fullest extent. Sometimes you have much more data than RAM would allow, and disk is bigger. But even then, you want to conserve kind of locality of code and stash most of the stuff in RAM as much as you can. What else? Network bandwidth. You want to minimize the number of times you have to go to the net, whether it's Ethernet or Internet or any other kind of network, because that's even slower than disk sometimes. The delay could be many seconds before you get a response from across the country on some website or database that's online in some cloud. What else? How about cache misses? You want to conserve those. You want to compute and try to minimize the number of times you miss a cache. How many know what cache misses is or caches? Okay, good. So I'm not being presumptuous here. What about page faults? Right? How many know what page faults are? You're doing paging, virtual memory. You want to try to conserve those because those go to disk anyway, and that slows you down quite a bit. And by the way, how much slower is disk than RAM? I think we asked that once. Let's ask it again, just so you know. It's very dramatic. How much slower is getting a byte from disk than getting a byte from RAM if you're a microprocessor, roughly? How many?
About
100 times? Well, it's at least that, sure. Any other thoughts? 100,000. Okay, so you upped it by 1,000. Any other thoughts? 400? So we have 100, we have 100,000, we have 400. What else? 1,000? Okay. Meta question. Why am I asking you that? Why is that important? Why should you know that, like cold, first thing you wake up in the morning, if you want to call yourself a programmer or a computer scientist? Why should you care about this?
It affects how you design your code.
Yeah. It affects how you design your code. If you don't know this number, you'll be writing code oblivious to this difference, and as if disk is as fast as memory, or only a little bit slower than memory, and then the code you'll design will crawl rather than fly. And that's not good. You won't be very efficient, and you won't even know why until you hear the actual number. So we're still not there. Any other thoughts about the actual number? How much faster is RAM than disk? I'm glad I asked that because it's a very fundamental question. And if you never thought about these numbers, you ought to. Every day that you call yourself a computer scientist, you have to know these numbers cold. Or at least their orders of magnitude. You know, the number varies slightly. But you can't be off by 3 orders of magnitude and still say you're in the ballpark. But you know, it's a bit like saying you walk into a restaurant, orders French fries, and you get the bill, and the bill says, oh, it's $4,000 for this French fries. And you'd be like, oh, okay, I guess I'll pay it. You know, you'll be in shock, right? It's really not $4,000, it's $4. So, you know, that's how dramatic 3 orders of magnitude error is, you know, in real life, and this is dramatic when you program, but when you program, you don't seem to be shocked by these discrepancies, and you should be. So, what else?
So I think RAM takes like nanoseconds. Hard drive takes about seconds. It takes about 9 minutes.
Yeah, so the access disk to RAM runs at roughly a gigahertz speed these days, or half a gigahertz to a gigahertz, roughly. So it takes about a nanosecond or half a nanosecond, you know, maybe 2 nanoseconds if you're running at half a gigahertz speed, you know, 2 nanoseconds, 2 billionths of a second to go to RAM and fetch a byte that you want to add to another byte. Okay, disk, how fast can you access a byte from disk? What's the seek time on a disk? It's on all the brochures and all the websites when you buy a disk drive. It says the seek time, average seek time is so and so. How much is it roughly? Don't you look at these numbers when you buy a hard drive or a computer? I mean, when you buy a car, don't you care how fast it can go, how fast it can accelerate, how many miles per gallon it gives you? I mean, you don't care? Right? Performance numbers? So how fast is it to go to disk to fetch a byte on average, roughly? What's a typical speed? All right, I'll give you 3 choices. Let's make it a multiple choice. Second, millisecond, microsecond, or nanosecond. And these 4 choices are 9 orders of magnitude off each other. The first and the last are off by a factor of 1 billion. So which one of those 4 do you choose to answer with? Second, millisecond, microsecond, or nanosecond? Micro? Okay, so he's going for 1 millionth of a second. Any other thoughts? I appreciate you. Whoever answers anything, I already give you credit for being a hero and speaking up. So you get points for courage. So don't keep silent. Say something. It's better than not saying anything at all. Yeah. Okay, micro, so you're backing up what he says? Okay. Any other thoughts? Why micro? Why not micro? Why this? Why not that? Why something else, maybe? A disk, how does a disk operate? Is it completely solid state? We're not talking about SSD solid state. We're talking about the traditional disk with a rotating platter. How fast is a rotating platter turn, by the way, on the disk, roughly?
If you're doing desktop, it's like 9,200 RPM.
9,200 RPM, sometimes 7,600 RPM. It's a few thousand RPM, right? So that means a few hundred revolutions per second is what we're talking about. Okay. How does a disk read something from this platter that's spinning at 10,000 RPM or less? How does it actually work? Is it it's just the platter that's spinning, or something else has to move?
It's got a read-write head.
It's got a read-write head.
Look at the etching in the disk.
Yeah, so a read-write head has to find the right track, and if you want to read random bytes from the disk, it has to move to different locations, and that read-write head is a physical piece of mass. It's a piece of metal and silicon and plastic and whatever else is in there, but it's a piece of mass that has to move back and forth. How many times per second do you think a piece of mass can move and accurately locate a track whose width is 1/100th the width of a human hair? That's with such high precision it has to find that track. How many times do you imagine that can happen per second? 1 million? It seems a bit far-fetched. A piece of mass can move 1 million times a second with with micron precision. So what do you think? How many times can you pull this stunt off in a second?
I know the SATA 3 interface is 6 megabits per second, or gigabit per second, and hard drives don't saturate that.
Right, but I'm talking about the seek time, randomly finding a byte. which means you have to move the read-write heading. You're not doing continuous block copies.
Like random I/O.
Random I/O on a disk, yeah. Just like random I/O on a RAM, you already said can happen about 1 billion times a second, right? At gigahertz speed, roughly, if the memory can keep up with that, and according to spec. But that's roughly the spec, about 1 billion times accesses to memory per second. So back to disk. A physical mass has to move with really, really incredible precision to find the right track. It's really, really much thinner than the human hair. How many times do you imagine a piece of mass can move per second? A few thousand at most, and it's really just a few hundred with that kind of precision. So the seek time is about 10 milliseconds, which is 1/100th of a second. So it can move, if you're lucky, it can move 100 times per second. That's it, 100 per second. So it's slower than a millisecond. Okay, next question is, how much faster is RAM than disk then? If RAM is gigahertz speed and disk is sub-millisecond disk access time, more than a millisecond. How many milliseconds, how many nanoseconds in a millisecond is basically what I'm asking you at this point. That's not a tough question. 1 million. How many get that? It's 1 million nanoseconds in a millisecond, okay? And a disk is slower than a millisecond. It takes about 10 milliseconds to do its thing per byte on a random seek. So a disk is 10 million times slower than RAM, 10 million. So if you want to store, fetch information back and forth, don't do it to disk. You're 10 million times faster. Not twice as slow, not 10 times, not 100, not 1,000 times as slow. You're 10 million times as slow. That's extremely dramatic difference. This is not subtle stuff here. This is complete universe apart in terms of efficiency. So I'm glad I asked that because most of you seem to struggle with this question, right? You should know this kind of numbers off the top of your head, last thing before you go to sleep, first thing when you wake up. It shouldn't be difficult. This shouldn't be trick questions to you as a computer scientist. If they are now, okay, work on this, and hopefully one day they won't be. So lots of resources you need to conserve as you go. We said power, space, time, accesses, cache misses, disk I/O. We just talked about that. Power and programming effort. So I don't want you to think it's just space and time. Although we'll focus this discussion here on space and time. When we prove some more theorems, you'll see that they apply to other resources besides space and time. All right, let's start with some definitions. A language is decidable within time big O of t of n if some Turing machine decides that language, and it always halts, and it always halts within t of n steps. N is the size of W. So this length of the input W is this n here. It's the same parameter, but here I'm denoting it slightly differently, just so you know that n stands for the length of the input. So it's big O notation. Big O notation is asymptotic notation, right? We don't count constants, just the growth of the function. Hopefully you all know what that is. We've used it before. So if a language is decidable within time big O of t, that means that language could be decided by a Turing machine that always halts within that time and does its job. It says yes if the string W is an element of the language, and it says no if the string W is not an element of the language, and it's always correct, and it works within time t of n. So t is an arbitrary function. It's a time bound, but it could be n squared. T of n could be n cubed. It could be the square root of n. It could be 2 to the n. It could be any function you'd like. But let's say it's a decidable function. It's a computable function for now. Weird things can happen if t is itself not decidable or computable. Okay. So that's what it means for a language to be decided within that time. How many get this definition? Okay, any questions so far? Because we can make the same definition for space. We can say L is decidable within S space, space big O of S of n, if, again, there exists a Turing machine that always decides membership in a language and runs using no more space than that function S, right? So these are two analogous definitions. They're parallel definitions. One is for space, one is for time. Okay, so far so good? Stop me if you have any questions, because very quickly we're going to build on these definitions. As you already know from this course, even when you step a few steps away from the definitions, you already could be in deep theoretical waters, right? Things compound very quickly as you move along from the definition. Okay, deterministic time, T of n, is the set of all languages decidable within that time, T of n. So now we're constructing not a language, but a set of languages. So this is DTIME, T of n is all the languages taken as a set. Each language is an element of that set. It's all the languages decidable within that time. And the D here stands for deterministic, right there. That's why it's called D. And N time is it if you allow non-deterministic Turing machines. Later you'll see why we kind of distinguish these two classes, deterministic time classes and non-deterministic time classes. Well, because sometimes they can be different. And sometimes they will be the same. And we'll prove theorems either direction about these things. And similarly, we're going to have the two space class constructions that parallel the first two. So these four definitions are not very different than one another. It's really the same definition, except pertaining to deterministic time, non-deterministic time, deterministic space, and non-deterministic space. But these are all classes of languages. In other words, they're properties. How many get that? They're properties, just like in Rice's theorem. Okay. Any questions about what these four definitions are, what these classes are, the fact that they're properties, quote unquote, why they're properties, because they're just sets of decidable languages, or recognizable languages even, and these are properties. Decidable is a subset of recognizable. So these are as good as properties. Of course, we already know that all properties that are not trivial are undecidable. So, but it doesn't mean that you can't decide any particular one, which may be easy to determine whether it has a property or not. But we're about to prove some theorems about these things and give a lot of examples. But that's just the definition so far. So far, we've done nothing but defined a few things. Question?
Didn't we say before that a non-deterministic Turing machine is more powerful than a deterministic one?
So sometime, in some scenarios, they'll be more powerful. Sometimes they won't be. And sometimes we don't know. And it's an open question. So the question P is equal to NP is exactly the question of whether something that's doable deterministically in polynomial time and something that's doing non-determinism in polynomial time have the same class of languages that it recognizes. So if you have deterministic polynomial time Turing machines and non-deterministic polynomial time Turing machines, recognize the exact same class of languages. And if it's true, then P is equal to NP. If it's not true, P is not equal to NP. And that's been an open question for 45 years. So sometimes it's not easy at all to determine if non-determinism gives you more power. And sometimes it is. Sometimes it definitely gives you more power and you can do more. Right? So for example, a push-down automata can recognize WWR palindromes non-deterministically, but a deterministic push-down automata cannot do that. Cannot recognize WWR. It can recognize $WR because it knows where the middle is and then can push, start popping the stack against whatever was pushed onto the stack. In other words, matching the last half of the palindrome to the first half of the palindrome. But in general, it's tricky to do. Determine whether non-determinism gives you more power in any one scenario arbitrarily. For finite automata, we know there's no more extra power. But now we started to talk about time and space usage. So extra power doesn't just mean can you now do it where before you couldn't, now that you're allowed non-determinism, but it means something more subtle, more difficult to ascertain than that, and it means could you do it with the same efficiency? Or does non-determinism allow you more efficiency? Right? Good question. Any other questions so far? Right now we just defined a few things. We haven't even stated a theorem yet, but we're about to. But let's make sure the definitions are clear in your head before we proceed. If there's no question, let me ask you a question. So you know what it means to consume a certain amount of time when you compute deterministically. It's the clock ticks. Right? You look at the clock on the wall, and if the clock ticks and ticks and ticks, and by the time you're done, you look at the clock and you say so many ticks have elapsed since you started, and that's your time consumption. Right? That's how long something took. And I'm deliberate to say ticks, not seconds, because these ticks may be nanoseconds, milliseconds, seconds, millennia, or just arbitrary time units. So we don't care exactly what the time unit is. These are just state changes in your machine. So how many states changed from one to the next? Okay, so for deterministic computations, you know what that number is, number of ticks. Now what about non-deterministic computation? Non-deterministic computation is a tree, it bifurcates, right, into multiple computation paths, and you have alternate state changes going different directions, non-determinism. So if a non-deterministic computation accomplishes something, and you have a computation tree, and some branches halted and accepted, other branches ran forever, other branches didn't accept, how much time did all this take? Different computation paths in the tree have different lengths. So what's the time measurement of this non-deterministic computation? We haven't said it explicitly yet, but let's nail that one down very tight right now, because it's actually inherent in these definitions. Here we say, some non-deterministic computation took, big O of t of n time. Well, what does it mean for a non-deterministic computation to take x time in general? Never mind what x is. What do you say to that? How do you measure the time? Yeah.
Would you base it off of the minimum path that accepts?
Yeah. So you take the path that accepted, and in fact, the shortest path that accepted, and that's your time consumption. And the other paths that didn't accept, or took longer to accept, you're not charged for that. Because some paths can take arbitrarily long to, and then accept. That's easy to construct such a computation. It'll just meander around, do a whole bunch of nothing, and then finally add the two numbers together and give you the answer. Right? That's easy to create such scenarios. So you don't want to be charged for extra stuff that's not necessary. Right? So you only pay for the minimum amount it takes to actually compute it in general, but not for all the inefficiencies of the non-ways to be thrifty or efficient. So that's what it means to measure non-deterministic time. The shortest path for acceptance in this non-deterministic tree, that's what you get charged for, not other things. Okay? What about space? Non-deterministic space, how would you define that? Different paths in the computation can use different amounts of space in a non-deterministic computation tree that's bifurcating all over the place. What do you think about that? Yeah, the number of cells used in the shortest, in that same path that we talked about the time, is how much space was used by that path that went the shortest. Okay, so that's how we measure space, non-deterministically. And if some other paths took a lot longer space, because you're doing all sorts of arbitrary things, maybe nothing to do with the computation even, you don't get charged for that, you don't get billed for that. So it's a sense of kind of fairness in what you get charged for. How much time or space you're using is sort of what you need to use and not what you're not using or don't have to use and so on. So I just want to make sure that's nailed down. Any questions? Any other questions? Yeah. If the shortest time and space path is what?
Are the shortest time and space path the same, or are they two different?
Not necessarily. He's asking a very clever question. He's asking, is the shortest path in terms of space usage the same path as the shortest path in space usage? And not necessarily. There could be convoluted cases where it's not true, where you use less time, but you use a lot more space. So for example, think in real life. What kind of data structure uses a lot more space but less time to do like lookups? Hash tables. Hash table could be huge, could be gigabytes of hash table, and you only store 3 things in it or 20 things in it, and you're wasting all this space, but the 20 things you can look up very quickly in constant time. So that's an example of something. So there's definitely time-space trade-offs. And we'll talk more about that specifically. Excellent question. Extra credit for that question. Submit that to the course website, to the form, extra credit right there. So if you ask clever questions, I'm going to give you credit for this. Encourage you to speak up and not just be quiet and be afraid to say something. Yeah?
Is it more common than not to have those two in opposition to each other?
Usually they coincide in kind of everyday normal computations. Things that take less time tend to take less space.
Seems like in our study of data structures that always was like that. Hey, you can do it with more space, but it's going to take.
Yeah, there's definitely trade-offs, but think about the following. You cannot use more space than you have time to use, right? So even initializing this hash table that's a terabyte long, just initializing it, how long will it take? Well, 1 trillion initialization operations to just zero it all out. And if you don't zero it out, if you don't initialize it, what will happen while you try to compute with this? There'll be all sorts of garbage there from previous processes, and you won't know how to distinguish your data from garbage data, and get all confused, and you won't operate correctly, potentially. Right? You start to look something up, and you say, oh, there it is, but it's not something you put there, it's something that was there before, and you won't know the difference. So you got to initialize it. The point is, you cannot use more space than you have time to use that space. Because the simple operation of just initializing all that space already takes that much time. Of course, you can use a lot more time for that space, but you cannot use less time than that space. So they are related. One upper bounds the other, but not necessarily the other way around. And there are trade-offs. Some of the trade-offs are pretty dramatic. Okay. So first theorem, time depends on the number of tapes in the machine. And the idea is that we already seen this before. If you have more tapes in your Turing machine, basically you can create higher efficiency when you compute. So for example, the language 0 to the n, 1 to the n can be recognized in quadratic time, deterministically in quadratic time. So in deterministic quadratic time, you can recognize 0 to the n, 1 to the n. How? Well, mark the first unmarked 0, then find the first unmarked 1, mark that, then go back, find the first unmarked 0, mark that, then find the next unmarked 1, mark that, and go back and forth, and mark the 0, and mark a 1, and mark another 0, and mark another 1. And by the time you're done, if all the zeros are marked and all the ones are marked, you know you have something of this form on your hand, 0 to the n, 1 to the n, and then you accept if and only if you ran out of zeros and ones to mark at the same time. But if you finish marking the zeros and you still have unmarked ones, it ain't one of those strings right there. And vice versa, if you have not enough ones and too many zeros, and you marked all the ones and you still have unmarked zeros, again, it's not one of those strings. Or if you have some 0 and 1 out of order, again, it's not one of those strings, and you reject in all these cases. That takes quadratic time. How many get this algorithm, by the way, of the marking? Okay, why does it take quadratic time? Because you go back and forth, and you traverse the whole entire input every time you mark one pair, and you have n pairs. So you traverse the entire input of length n. You do it n times, so it's n times n. That's a quadratic time algorithm. So we just place this language in the complexity class deterministic quadratic time. Any questions about that? We just proved that that's the case. This language is in this class. Remember, these classes are classes of language. They're properties. They're sets of languages. So each one of those has a type that's a set of sets of sequences of symbols. The type is nested for deep. Just keep that in mind. Now, why am I saying it's also in linear deterministic time if you have two tapes? Because this was true for a one-tape machine. You had to go back and forth and back and forth, back and forth on the same tape because you didn't have a second tape. But if you had two tapes, you could be more efficient. Take the input, copy it to the second tape, then march along both tapes. One tape you'll march along the zeros, the other tape you march along the ones, and as you compare them pairwise, in one linear sweep, you can make sure there's equal numbers of zeros and ones, and you're done, and you just spent linear time only, not quadratic time. How many get that? Okay, any questions about that? So we just placed this language in two different complexity classes, DTIME n squared and DTIME n, which means we place it in quadratic deterministic time and in linear deterministic time at the same time. So this language is in both of these classes. This class is not necessarily disjoint. In fact, all of this class is a subset of this class. How many see this theorem? Right? Because whatever you do, whatever you can do in linear time, you can also do if you had quadratic time. If you have more time or more space, you can do whatever you could do before with less, and perhaps more, but you can't do any less than you could before if you have more resources, right? So, if you're a millionaire, you can buy a bunch of stuff. If you're a billionaire, you can buy all that stuff and perhaps many more things. But if you're a billionaire, you can't buy less than what a millionaire can buy because you have more resources, not less. So it's monotonically increasing. So if you increase the time or the space up, You can do whatever you could before and perhaps new things as well. Okay, it gives you more capability, more capacity, more options. Okay, so for a two-tape machine, we see how the time dropped from quadratic to linear pretty straightforwardly, right? So we're saying that the time could depend on the number of tapes, okay? And by the way, when we have multi-tape machines, we're not charging you for the space that the input requires. So the input space, the space that contains the input string that is given to you at the beginning of the computation, that you don't get charged for. That's a freebie. Because you have to be given an input somehow, one way or another. And by not charging you for the input, not only it's fair, because the input always has to be given to you somehow, but it gives you another advantage, and that is you can only, if you only charge for the extra space that's used beyond the input, it allows us to analyze sublinear space requirements, like logarithmic space, square root space, space n to the 2/3, space log squared, space log log, whatever, sublinear. These are all sublinear spaces, less than linear. So it gives you more option, more analysis capability, more fine-tooth kind of analysis capability to analyze sublinear space requirements as well. Okay. Space, on the other hand, is tape independent. So we just seen that space, the amount of time you use depends on the number of tapes. The amount of space you use doesn't depend on the number of tapes. And the reason is, if you have several tapes like this, tape 1, tape 2, tape 3, each one with its own read-write head, and they're all moving independently, and that's how much space you use. This space plus this space plus this space is all the space that you're using. What you can do is you can merge or interlace the three tapes together to a single tape, and you're not using asymptotically more tape than you're using before. You may be using more time than you're using before to jump all over this single tape. And by interlace, here's what I mean. You take these three tapes and you interlace them, you zip them together like this. You want to see it again, instant replay? There we go. I'm proud of my PowerPoint animations, you know. Now you know how I spend my weekends, sort of. So what technique is this, by the way? One word? You want to buy a vowel? Somebody who didn't participate today yet. Let's get some more people. What do you say? Dovetailing. How many see dovetailing going on? Good. So you interlace these tapes, and to simulate these three tapes with one tape, you can go back and forth and simulate these three tapes with a single tape. But to simulate this tape, if you're here, the read-write head on this tape can make this change, because this is the read-write head for the blue tape. For the red tape, you then have to march all the way across to here and make this tweak. And then for the green tape, you have to march wherever that is and make that tweak. And you have to go back and forth, possibly cross this entire region of the tape just to do one state change simulation of the original three-tape machine. How many get that? So the total amount of work you're doing here back and forth in terms of time, not space, how much more time are you using than the original machine potentially in the worst case? Take a wild guess. By being forced to go back and forth. How much more time consumed it is. If the original takes time t of n, this simulation can take time what as a function of n? Quadratic, that's right, n squared, he's right. Okay, how many see n squared kind of going on here, in the worst case, potentially? So you actually, so this is a space-time, kind of trade-off in a sense, right? If you're more space constrained and you don't have direct access, you may have to spend a lot of time doing this. In real life, this happens all the time, by the way. I'll give you a couple examples from real life. One is, if you have a lot of stuff in your house and your cupboard if your closet is just full of stuff to the brim, there's no like walking space in your walk-in closet. Everything is just stuffed. And you're looking for that pair of shoes that you know is in there, but it's buried under all these other things. And now you have to start removing a lot of things from the closet. Finally, you see the pair of shoes, you take those out. Then you put all that stuff back in the closet. And you did all this work just to pick up a pair of shoes that you know is there. In fact, you even know where it is there, but it wasn't accessible right away. Right, so it's, and then if you want another pair of shoes or some other, your umbrella or something, and it's stuck there folded in the closet, again, you have to do all this extra work just to fetch now the umbrella. And the amount of time you spend if your house is just full of stuff could be quadratic in the amount of stuff you have. If you want to, how many understand this? And you've experienced this, and it's inefficiency. Right? On an airplane, you experience that too. You always have a small amount of space on an airplane in front of you, a little tiny table that's 1 square foot. Right? And so you could put your laptop on there, but then the meal comes, so then you have to remove the laptop and put the meal there, and then a drink comes, so then you have to get this thing off, and so you can put the cup down, and then where's your laptop, and you have to wait and then remove the meal tray first, and then put the laptop back on. It's very inefficient to have such a tiny amount of space in front of you, and you waste a lot of time utilizing that tiny little space. It's a time-space trade-off right there. Right? How many experienced that in your life? So you know what I'm talking about. And these Turing machines experience the exact same phenomena. You have a tiny amount of space to compute. You have to spend all this time kind of jumping back and forth, rearranging things as you go, when if you had a lot of space, you wouldn't have to do all that. You could just spread it out, and it'll be fine. Okay. Any questions so far? Okay, so we're going to get more and more subtle as we go. So here is a theorem that just explains what we just discussed. So a one-tape Turing machine can simulate a k-tape Turing machine with a quadratic jump in time consumption. So what he said is this theorem right here. You take T of n time to do something on a one-tape machine, you move to on a k-tape machine, here k is 3, you move to a one-tape machine, you can interlace, sure enough, dovetail, but you're going to pay quadratically now in the original time complexity. And there's also a factor out here of k. Why? Because even if you didn't pay quadratically, to get from this one to this one to this one, here they're all juxtaposed adjacently on this tape. 1, 1, 1, 1, green, 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 green. Here the greens are 3 apart, and there's k tapes, so k is 3 here, and so here on this tape they're 3 apart, the greens. Green, green, green. The blues are also 3 apart. Blue, 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 blue. So you're paying a factor of k in addition to a quadratic factor that's a multiplicative factor of the k, just so you know. So it costs you, yeah.
Does it have to move one at a time, or like this? You learned that like an array is constant time?
Yeah, so an array, yeah, but this is not an array, it's a Turing machine tape.
But it can't just jump?
No. And if it could jump, it still will jump in k steps to get to where you are. So the jump really is k things juxtaposed, k state transitions done back to back. So the jump really is individual steps. So you're walking, you're not jumping here. The read-write head can only move 1 square to the left, 1 square to the right, or stay in place. That's all it can do. That's what a Turing machine does. That's all it does. There's no jump operator defined in a Turing. If you're not sure, look at the definition of a Turing machine. There's no provision for big jumps or other more complicated operations. All you can do is change a state and move left or right 1 square. So you're kind of restricted by that. Yeah. Question.
Why are we using big O as opposed to big omega or big theta?
Why are we using big O here in terms of the time or space complexity, not omega or theta or little omega or some other or little o? Because we want to upper bound the time and space. So it's the same reason we use big O for algorithms. So if I give you a problem, come up with an algorithm to sort a bunch of numbers, and then you come up with, I don't know, bubble sort or insertion sort, and I say, okay, how fast is your algorithm? You would express your answer in terms of big O. You'll say it doesn't run any slower. The maximum amount of time it would take to run is big O of n squared, say for bubble sort or insertion sort. How many heard of bubble sort, insertion sort? Good. So it's quadratic time to sort. Now there's faster algorithms to sort, like merge sort. It takes n log n time, and then you say still it's big O of n log n for merge sort, or heap sort, or some other sort that takes n log n time only to sort. But it's the same reason you'd use big O for algorithmic descriptions. You want to give me a gross upper bound, a guarantee, an assurance that it won't take longer than that. And then I'm saying, okay, no worse than quadratic, okay, I'll take that, because at least it's not exponential. or something worse than quadratic like cubic or something else that's bigger than quadratic. So you want to give an upper bound and explain that it won't take any more time or space than that upper bound. So it's a guarantee, it's an assurance. It's a nice feature to know about an algorithm or a Turing machine, because after all, a Turing machine is an algorithm. So it's not a coincidence that we use the same kind of notation to talk about Turing machines, time and space consumption, as we do about algorithms, because Turing machines are algorithms, actually. For every algorithm you can think of, there's a Turing machine that implements that algorithm, and vice versa. For every Turing machine, there's an algorithm that simulates that Turing machine and does exactly what it does. So Turing machines and algorithms are synonymous. So that's sort of the intuition here, why we use big O here, because these are essentially algorithms. And you already know how and why we use big O for algorithms to describe their time and space and resource consumptions. Okay, any other questions? That's a good question. Now, in some scenarios, you'd use omega also, right? In algorithms, you also use omega, right? So to finish this example of bubble sorts, a bubble sort runs in time big O of n squared. But if you want to express it as omega, what will be the omega analog for bubble sort? Well, but yeah, so there's an n log n lower bound on sorting in general, but on bubble sort specifically, how long does bubble sort takes to run in the worst case? It could be more than what? N squared. So it's also theta of n squared, so you could talk about it that way too. And in Turing machines, we can also do the same thing. Sometimes we can invoke omega and theta and, in the appropriate context, and not just upper bounded with omega, big O, but lower bounded with a theta, and then if the two shall ever meet, lower bounded with omega, upper bounded with big O, which is omicron, the Greek letter, omicron, and if the two shall meet, then it's theta, it's an exact bound. And this happens in Turing machines as well as it does in algorithms. But the default is big O for algorithms and here. Lower bounds are hard to prove. Why is it hard to prove a lower bound? He mentioned that for sorting, there's a general theorem that says comparison-based sorting can happen not any faster than n log n, omega of n log n. That's a lower bound for sorting in general. Why is it hard to prove lower bounds? It's a non-existence proof. You're trying to prove you're not a millionaire. That's hard to do. You're trying to show something doesn't exist. Out of all the infinity of possible ways of doing it, you want to show that none of them can work faster than this bound here. That's the lower bound. In general, that's hard to do. You want to prove something about an infinity of objects as opposed to just one counterexample. It's hard to do. So, and it's hard to do for Turing machines for the same reason it's hard to do for algorithms. All right, more theorems. If you have more time, if t prime of n is bigger than t of n for some two functions, t and t prime, then DTIME t prime is a superset of DTIME t of n. In other words, if you have more time to compute t prime, you can compute at least as many things, languages, as you can compute than if you had less time to compute them as a bound. And same for non-deterministic time, and same for space. So we already mentioned this, but now we're stating them as theorems. If you have more time or more space, either deterministically or non-deterministically, you can do at least what you can do before and possibly more, and that's why you have a subset containment there between the two sets of languages, the classes, the properties that are deterministic time t and deterministic time t prime, which is bigger than t. How many understand these two theorems here? Not far-fetched, right? If you have more resources, you can do no less than before, and possibly more. Okay, so that's straightforward. So for example, all of the non-deterministic time linear is contained in non-deterministic time quadratic, right? Because if you can do it linear time, certainly you can do it within quadratic time, because that contains everything below quadratic. And if you want to use exactly quadratic, fine. Then solve it in linear time, then waste quadratic time right afterwards, and then you'll be solving it in exactly quadratic time. So for example, in the case of sorting, back to sorting, could you think of a factorial time algorithm for sorting? Give me a sorting algorithm that runs in time n factorial to sort n things. Which one? Bogo sort, yeah. What would the algorithm look like? Instead of just wasting factorial time, let's actually make it not as bogus as that. I'll give you one. You want to sort n things? Good. Look at all permutations of the n objects, see which one is monotonically increasing, and print that one out. How many see? That will sort. This is correct sorting out. It's just very slow. It takes n factorial time because there's n factorial different permutations. So you can always use more resources if you want to. So that's what these theorems say. If you want to use more time or space, you're welcome to it. You don't lose any languages over it. You're just becoming less efficient. And possibly you can recognize new languages that you couldn't recognize before. All right, let's get more specific. So let L1 be this language 0 to the n, 1 to the n that we know is not context-free. Excuse me, it's context-free but not regular. We've seen that before. You can prove that using pumping. So this language is in deterministic time quadratic. We already mentioned that a few slides ago. We can go back and forth, match zeros to ones, cross them off and know that they're an equal number, then you're good. Right? But you can also put it in deterministic space linear. Why deterministic space linear? Because this algorithm that we just mentioned by crossing off a 0, crossing off a 1, yeah, it takes quadratic time, but it also takes linear space because you're only marking the input repeatedly. You're not using any extra space than that. So we just placed this language, L1, in deterministic quadratic time and in deterministic linear space at the same time. How many get this? So we just proved these two. I'm reluctant to call them theorems because it's pretty straightforward, but that's what we just proved. But let's do something more interesting. Let's place this language, the same language, L1, in deterministic time n log n. How would you solve it in n log n time? Not in quadratic time, which we already did by crossing off a 0 and a 1, another 0 and another 1. How would you solve it in n log n time? That one is not so obvious, right? But I'm suggesting it's possible. And I'm asking you, why? Why can you expend no more than n log n time to solve this problem, to recognize this language? Yeah.
One, you can do it in linear time and space time. But I was going to say for the space thing,
Yeah.
wouldn't it be constant space because you said earlier that this space given to us as part of the input doesn't count?
Yeah, so very good point. I said the input space doesn't count, but I didn't say you can modify that input space. The input space is read-only. So you're not getting charged if all you're doing is reading it. But if you're going to start writing to it, now you're using it. And now you're going to be charged for that. It's like you touch it, you buy it. You know, essentially is what we're saying. If you're just looking at it, it's okay. You touch it, you buy it. You get paid, you get charged for that. That's a very good point, actually. How many get what he said? Good. Another way of thinking about it, you can touch the input space and not. What you can do is, if you have two tapes, for example, you can copy the input to the other tape, not touch the original, and not get charged for that. And you can touch the copy, and you get charged for that. But that's the same as touching the actual input. But what you did accomplish there is preserve the input for later in case you need to refer back to the original input. You still have a copy of it. But just by copying it over to another tape, you've already expended linear time, and linear space for that matter, just by doing the copy. So you didn't really save anything by copying it. You were charged for that. And if you charge it in place, if you modify it in place, you charge for that too. That's a very good point. Okay, back to this. How do you recognize this language in n log n time? Using a Turing machine with, say, one tape. And you can modify the input if you'd like. Or even if you have two tapes. Well, if you have two tapes, you can do it in linear time. We already know that, right? We already proven that in linear time, right, you can do it for a two-tape machine. We said that right here a few slides ago. So let's do it on a single tape machine in n log n time, right there. So I'm saying it again here. For a two-tape machine, you just copy it and then go across the zeros, across the ones on two different tapes. And in linear time, you can match their numbers, make sure they're equal. But how do you do it in n log n time on a single tape machine is what I'm still asking. Any thoughts on that? You see how it's, now we're getting algorithmic here. I mean, we were algorithmic all along from the beginning of the semester. All these simulations and converting recognizers to deciders and deciders to recognizers and electrographic orderings to recognizers and back and forth. These were all algorithms in a sense. Even the proof of the halting problem was an algorithm in some sense, right? If there was an algorithm for the halting problem, we can use it in another algorithm by calling it a subroutine and blah, 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 and then that proves that there's no algorithm for the halting problem. Otherwise, you come up with a contradiction. Now we're getting even more algorithmic than that. We're asking for an algorithm to recognize 0 to the n1 to the n on a one-tape Turing machine in n log n time. Right? What do you say? Oh, yeah, go ahead.
Recursive algorithm, maybe like find a position in the middle, it's going to happen.
So he's saying recursive algorithm is it's a nice try, except, first of all, Turing machines don't do recursion unless you implement a stack and you go back and forth and do it the hard way. But now you're wasting a lot of time doing that. And then how would you find the middle? A Turing machine can't find the middle of something arbitrary. It has to compute where the middle is the hard way by first measuring the entire thing, storing that value somewhere, and then advancing in half that value after doing the division by 2. So you can do all that, but it's going to cost you. You can't just say it and it'll arbitrarily do it. You're going to implement it the hard way. Okay, what do you say?
Can't it just move right until it sees the first one and then start from the right close to 0 and then start from the middle that way?
He says, find the first one and then keep, what, canceling ones against zeros?
Yeah, so it only needs to move back and forth like first 1 time and 2 times. 2 steps.
Oh, okay. So he's saying, interesting idea. Let me paraphrase what he's saying. So he's saying, if you have a bunch of zeros here and a bunch of ones, he's saying, you know, first go and find the first one, and then cancel it against the 0, and then find the next one, and then canceling against that 0, and then basically move back and forth like this, right, is what he's saying. And yeah, you can do that. You can cancel this one against this 0, and then go back here, and then go back here, and then go back here, and that your path will be meandering like this, right? How much is the total length of this path in terms of the original length of this input? How much longer is this path than this path? If this path is n units, how long is this meandering path if you stretch it all out? If you unfold it? If it was n log n, would be good. This will be an algorithm. But I'm implying that it's not n log n. So what is it?
I think it's n squared.
It's n squared. It is quadratic. Why? It doesn't look quadratic. Quadratic would be like this, right? If it was pure quadratic. This path length here is quadratic. The length is n, and there's n of them. So it's n log n, it's n squared, n times n. Why is this also quadratic, even though it doesn't look it? Yeah.
It's like if you add all the numbers from 1 to n.
Yeah, it's if you add up all the numbers from 1 to n. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, as opposed to n plus n plus n plus n. So n plus n plus n plus n times is quadratic, is n squared. But 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 all the way up to n, that's also quadratic. How many understand that? Prove to me it's quadratic. In one sentence, go. Prove that sum of integers is quadratic. We've actually done this in the first lecture of this class. How many remember that? Do you remember what the proof looked like? Describe it in a few words. What would the proof look like? Staircase. How many remember the staircase? The blue-red staircase. Right? So we had a staircase that looks like this. Right? The area of the staircase is 1 plus 2 plus 3 units, right? Plus 4 units plus 5. So the area of the staircase is the sum of integers. But what's the area of the staircase? Put another staircase on top of that. right? And these two staircases, there's n this way and n plus 1 that way. So it's n plus 1 times n divided by 2 because it's two staircases, not one. I mean, remember that proof. So this proof you'll never forget in some sense, this staircase. Remember we talked about visual proofs, elegant proofs, proofs that are easy to intuit about, that kind of grab your intuition, leverage your intuition. So this meandering path is exactly this business here, about this staircase area, which is sum of integers, which is quadratic. So that algorithm is quadratic, but it's a good try. All right, how do you get n log n? We're back to the original question. I appreciate people who speak up. You already get points for courage. You know, it's not easy to say something in a crowd, right? I'm used to it, but you need to get more comfortable with it. It's a good thing. All right, n log n, what are we looking at? How would you do it? So basically, you can no longer eliminate things in pairs and spend linear amount of time just to eliminate one pair. That's no good, because that will take you a quadratic amount of time to eliminate all pairs. We're trying to get away from that. We're trying to get a total of n log n at most. So how will a Turing machine do it? It's an honest-to-goodness algorithm questions. You can say that about, you can pose it in a programming contest as an algorithm question. Right? What do you say? Okay, that's a good comment. She's saying log n usually suggests some sort of splitting of the space, a divide and conquer in general, like merge sort. That's a good thought. What do you say?
Build off that. What if you could find the middle of the zeros? It's okay, I got half the zeros, now I have half the ones. Match those, eliminate, and take the remaining half, split them up.
Yeah, so he's saying match half of those to half of those, and then recursively or inductively match other things. But the thing is, you still have to walk across a long ways to get this to this other half. And this back and forth of walking across, you want to minimize it. And you don't have place to store the number of zeros that you see in the half of the string, because there's no registers, in the Turing machine, and no counters per se. You can implement them on a tape, but then you have to walk away over to the counter and implement that, and then walk back, and that's going to cost you too. Yeah.
So as you're reading through the zeros, could you read, for example, 2 zeros and replace it with one symbol that means 2 zeros crossed off?
Yeah, so he's saying cross off 2 zeros, replace it with a single symbol, and you can do that, but that single symbol is still right there, and then you have to walk across a long ways to eliminate 2 more ones on the other side, and then walk back, and so you're still walking long distances right across the entire input, or most of the input, just to eliminate 2 zeros, or 1 zero, or even 3 zeros at a time. Let's take the next logical leap beyond that. Yeah. What do you say?
So starting from the beginning, you combine the first two like he said, and then you put a new symbol at that slot, say a 2, and then combine the 2 and put a new symbol at the next slot, and then until you get to the 1s, and then go across.
So then you put a 3 and then a 4?
Yes.
Okay, so he's saying keep a count of how many you've seen and make a new symbol equal to that count.
Make that symbol override the one to the right.
Yeah, so again, it's a very good try, but then you'll need a symbol for a 4 and a symbol for a 5 and a symbol for a 17 and a symbol for a million. How many symbols will you have in general? How big is your alphabet is what I'm asking. Infinite. The alphabet must be a finite set of symbols, right? The word finite is hard-coded into the definition. You can't have an infinite alphabet. If you could do this kind of trick. It'd be a nice trick, actually. But the alphabet is just 0, 1. And maybe a couple other characters that you use for marking or something. But you can have arbitrarily large alphabets. But that's a very good try, very good trick if we could pull it off. All right, what else? So at this point, we're programming Turing machines. We're hacking Turing machines, right? This is where JFlap comes in really handy, where you can try different things and see how it works and whether it works and how fast it works and so on. But, all right, let me give you a hint. unless you want to go more at it. So here's a hint. Try in linear time, eliminate not 1, 0 and 1, 1, not a single pair, but eliminate half the pairs in linear time. Eliminate half of the 0, 1 pairs. Eliminate half the 0, mark them off. Mark off half the zeros and half the ones and not take more than a linear amount of time to do it. How would you do that? If you could do that, how long will the rest take? If you can eliminate at every phase of this algorithm half the zeros and half the ones, and by half the zeros and half the ones, I mean half the remaining unmarked zeros and half the remaining unmarked ones. If you can mark half the remaining unmarked of both the zeros and the ones in linear time, how long before you'll run out of things to mark? It's not a trick question. Log n, logarithmic time. And if you run out of zeros to mark and you run out of ones to mark in log time and each phase took you linear time, the whole thing will be n log n time. So the remaining question is, how could you accomplish this task? How can you mark half of the remaining unmarked zeros and ones in linear time? It's not hard to do, but you got to say something. Silence is not an algorithm. How would you do that? Yeah. So what would you do? Yes. Mark every other 0 and then mark every other 1. And in linear time you can do that. And you don't need extra symbols to do that. And you don't need a lot of counters, or you just blindly jump and mark every other unmarked 0 and every other unmarked 1 in one fell swoop in linear time pass over the entire input. Then what do? After you do that, you do it repeatedly, right? And if you do it repeatedly, at the end, you'd exhaust all the ones and all the zeros in logarithmic number of passes. Because if you eliminate half, and then half of the half, and half of the remaining half, and so on, there's only a logarithmic number of times you can repeat this before there'll be none left. Right? How many get that? That's how tournaments work. How many understand that statement? Right? You have a bunch of teams or players, and at each round of elimination, half of them lose to the other half that win, and only those continue to play. And if you have n teams, how many rounds do you have? How many elimination rounds? Quarterfinals, semifinals, finals. How many of these elimination rounds do you have in a sports tournament? And it doesn't matter which sport it is. Tennis, basketball. How many rounds if you have n teams? Again, not a trick question. 2 to the n, really? So if you have 20 teams, you'd have 2 to the 20 rounds of elimination? That would be a very long tournament. No, I mean, I assume there's some sports fans in the audience, right? Yeah. It's log. Right? Log base 2 specifically. That's good. Right? At each round, half the players or teams or whatever sport it is get eliminated, and then half of the remaining ones get eliminated. And how long before you can declare a winning team or a winning player? If it's tennis, is one player that can beat all the other players. After a logarithmic number of rounds, you'd get to 1. Right? The same thing here. Right? You eliminate every other 0, every other 1 on the tape. So just to be sure, let's write it out, since it seems a little mysterious to you at this point. So here are the zeros, and here are the ones, right? So we're going to eliminate this one, and this one, and this one, and this one, and then eliminate this one and this one. I'm going to skip every other one, right? I guess this one. And then I'm going to eliminate every other remaining unmarked. I'm going to eliminate this first one, but not this one. Eliminate this one, but not this one, and so on and so on. How many get this algorithm? Okay, any questions about this? So in n log n time, you'd know that the string is of this form, 0 to the n, 1 to the n. And this is not the complete algorithm. There's a couple of things you got to do, right? Let's say you eliminate, and all the zeros are now eliminated. Are you done? Could you accept that string? What is the real condition at the end where you can accept versus reject? It's a little, there's a little bit of detail there we left unsaid, so let's say it. If there's anything left unmarked, once you mark everything in the zeros, you want to make sure that there's no ones left. And conversely, if you mark everything in the ones, make sure that there's no zeros left. And if they get both exhausted at the same time on the same round, you know that we're in equal numbers. Nowhere in this algorithm did you count the zeros and count the ones and compare the counts. How many understand that? We just blindly eliminated half of each and kept going, and the two would be exhausted simultaneously if and only if they were the same number to begin with, and we didn't have to count them. So just because the definition counts them, n of these and n of these, doesn't mean the algorithm to detect that condition must count also. Remember examples that I showed you, a language, the language is equal to a string yes if Trump wins the next election cycle, and it's 0 otherwise, and I asked you if it's regular, and you said, well, it's not regular because how will a finite automata be able to predict an election, even if experts can't predict election? Well, the point is it doesn't have to predict anything, it just has to be right. So one finite automata says yes or 0, one finite automata accepts the 1, one of those two will be right, and so one exists, so the language is regular. So again, you can take some shortcut, get away from the definition, and still accomplish the job, and not follow exactly how the definition is defined. So this wasn't trivial, I admit. This was a bit of an algorithm, and it took some cleverness to reduce it to n log n. Could you reduce it to linear altogether? Can you put this language in linear time? It turns out you can't. It turns out this n log n is also a lower bound. It's an omega, as well as a big O. And also another lesson here, just because we can easily place it in quadratic time doesn't mean we can't place it in some lower complexity class with respect to time. Okay? Now, it's obvious how to do it in linear space, but how do you do it in logarithmic space? Logarithmic on the second tape, not the input space. Okay? So this I'll give it to you for extra credit. Right? So for extra credit, find out how to place this language in logarithmic space. Not to expend more than logarithmic space. Because spending a linear amount of space is easy. Copy the input, and then on the two tapes, measure the ones against the zeros, cross them off in pairwise in lockstep, and you'd be done. But how do you pull this stunt in logarithmic space, not linear space? And I'm suggesting to you that's possible. Otherwise, I wouldn't be asking you to do this. For extra credit, put L1 in deterministic logarithmic space. And next time, we'll prove lots more theorems and lots more examples. And now we're into complexity theory. Okay? And this is going to get deeper and deeper. So please solve lots of problems. Finish the midterm by Sunday, and soon there'll be another assignment posted, and it'll be fun. All right, see you next time.